today, continuing with the last little bits of sampling. There was one important topic I forgot to cover last week. And then we'll kind of just move into some additional creative techniques for working with samples. Today, it's going to be a little bit of an improvisatory teaching day, but I have on the agenda filters and possibly granulators, although that is kind of a lot to cover. And then next week we will start in on sequencing and all of the rich tools that are available in SuperCollider for structuring sounds in time. So, kicking things off, we're going to boot the server, and we are going to load this sound file. As a reminder, I've got in my week 6 folder here, I've got the code file which I've saved and this audio folder of stuff. And we are loading this prayer bowl sample. We'll just play it. Very nice. Okay. So that is in and loaded. And I have a synth def, which has just been copied from last week with some very, very, very minor changes. They're essentially exactly the same. And then a synth. So we can load this synth def. And we play a buffer. We also create an amplitude envelope, which is applied. It's got a finite duration with a done action 2. We also have a global amplitude control, and we send it on out. So, yes, question.
For the arguments for like amplitude out, do we need the control rate?
Well, it's a good question. The question is, do we need the control rate for these arguments? The question is, do you see yourself changing the amplitude of a synth while it is playing? If yes, you must use either control rate or audio rate. But if you are content to every synth you create, if you are fine with a 100% constant amplitude value, then we don't need KR and we can use IR if we want, and that will save us some CPU power. And in this particular case, we're dealing with a finite envelope. So we're going to play a sound with an amplitude envelope and it's going to die away. So honestly, it might be a pretty reasonable thing to do, to use IR over here. And really for all of them. So it's, for one reason or another, I'm just in the habit of using KR because I tend not to bonk into the CPU ceiling, even if I have lots of large synth defs with arguments all running at KR. But yeah, that's the only thing. If you want to be able to modulate this dynamically while a synth is alive, it's got to be KR, at least. All right, so yeah, we have our synth, and we can use MIDI ratio to transpose. And any of these other arguments, we can start somewhere randomly in the buffer. We could pick a different buffer if we have loaded other buffers in here. Change the amplitude. You get the idea, right? This is all stuff we've discussed last week. The first thing I want to talk about today is the fact that absolute paths are problematic. If I send you this code, in fact, if I send you, if I take this folder, this week 6 folder, zip it up as a zip file, which contains the code and the audio files, and then you open up this file on your computer, this code will not work because the path is wrong. This is a specific path to a location on my computer. So you can see the issue here, right? You have a collaborator or a performer or somebody, and you send all of your assets and your code and your audio files and everything to that person, and they'll say, hey, your code doesn't work. It's broken, right? And in a sense, they're right. It is broken because your path is wrong. So how do we fix this? I need to somehow anticipate what path this should be on somebody else's computer, which I can't really do that. But what we can do is specify the path to a file as a relative path rather than an absolute path. And there are 2 ways to do that. And the first step to doing that is to make sure that your code that reads the file and the files themselves are in the same location. And they are. They are both in this folder called week 6, 2022, 929. So that's good. All right, so one option is to use the method resolve relative, which essentially takes a partial string representing a file or a folder of files or whatever, and it will use the location of the code file in which that code is being evaluated as a reference point. And it will fill in the back end of that path. So if I just say blah dot resolve relative, what this returns is a new string, users, Eli, documents, et cetera, all the way up to the folder that contains this file, and then it tags on the rest of the stuff. So instead of blah, we want to say audio / prayer bowl AIF, because that is the folder, that's the file we're interested in. Like this, right? And that gives us the exact same path that we were working with up here. So just get rid of that buffer for a moment, right? Gone. And we can say b equals buffer.read. There we go. Now, we're doing the same thing, but we've dealt with the problem of this path being incorrect on another computer. So now we do this. I guess it was like queued up to play or something like that, right? So it works now, right? Can free, load this, and there it is again. So that's resolve relative. Does that make sense to everyone? We give it just the part of the path that is specific to its location, right, in the folder that contains both the code and the audio. And then we just provide the tail end of the path, and resolve relative fills in the rest. So now, if I send you this repository of code with the SCD file and the folder, and you open it up, this line of code will work. I kind of recently discovered this. The other technique I have used in the past, and which is the technique that I tend to use on lots of the videos on my channel, is this process, which is a special keyword, in the same way that true and false are special keywords. You see it turns purple, right? Dot now executing path. And this expression returns the absolute path to this file. And there it is. So it's not quite what we want in terms of our buffer audio path, but it's close, right? We have all the way up to the folder that contains our project, and then the SCD file itself. So we have to kind of go back one level, and then go into the audio file, and then into the prayer bowl file. And so what we do is we wrap this in a class called pathname. This is a utility class, which gives us access to files and folders on our computer. So we create a new pathname. There it is. It looks exactly the same. It's just a pathname object that represents this file. And we can say .parent path. And this gives us a string to the parent folder, right? One layer up in the folder structure, and then we can tag on audio / prayer bowl.aiff. And so this expression is also a valid path to the file that will work on anyone's computer. So we can say here, we could even say something like path equals this business, and then b equals buffer.read s path. Could even bundle this together if we want. Right, so just to confirm, free everything, all the buffers, run this, and it works. I think this is a little bit cleaner. It's a little bit shorter. So that's probably what I'd recommend, but it's good to be aware of this process.now executing path as well.
Can you also use like // and //?
Can you use // and // I I'm trying to remember. I'm not sure. We could try. So you mean for here we would say, yeah, okay. So something like, trying to think of the right way to do this. This process dot now executing. I don't know. You can try it out. So if we say something like, I don't know if this is going to work. I don't know. I think it might depend on a few different factors. At least in this context, it's just going to add the characters to the string. I don't know if it will actually interpret it correctly. But yeah, at least this I know will work. Good question. And try it out. Let me know if it works. I'm not sure. Okay, so this is actually the first question on your homework, which is due next week. I give you a buffer, an audio file, which you're supposed to read into a buffer. And the first question is, use one of these techniques so that when I'm grading your homework, I just run your code and everything works. And this is the way to do it. Okay, good? Moving on. Let's take a look at this synth down here. And let's see, what we're going to do here is first take a look and ask ourselves, are there any improvements that we might want to make to this synth? Anything at all? Here, I'll give you a clue. Volume's okay. Volume's not too big of a deal. It's peaking around -20. I mean, we already have an amplitude argument, so should we want to make it louder, we already have the ability to do that.
Only coming out of one channel.
It sure is. It's only coming out of one channel, right? So let's fix that. Right? Now we could just do this and call it a day, right? But that's not very interesting because then it's always going to come out of both channels, right? Maybe we want the ability to spatialize this in stereo. And we can see that our play buff is a one-channel play. It's a one-channel signal. So we can use pan 2. Right? Add a pan argument. And now we can play it. The default is 0, which is in the center. Or we can also say left, right, and sort of on the right, sort of on the left. That's good. Anything else we want to add here? I'll tell you what I notice. The envelope is always the same. Specifically, the durations of the segments are always the same. There's always a 0.02 second attack imposed on the sample and a 3-second release. So let's do this.
What is IR again?
Initialization rate. It's a sort of unusual that it's even called a rate at all because it's just one value. When an argument is running at the IR, it calculates exactly one value when the synth is instantiated, and then never changes. It's not settable. And I think it makes sense to use those here because once a synth goes into existence, it doesn't really make sense to change or modulate the attack time, which has already happened, And like it doesn't. It's just these values are only checked when the envelope is initialized or reset with a trigger. And that's just never going to happen. So, but I do want to be able to set these when a synth is created. And we can't do that if these are just fixed numbers. But if we make them into arguments, even if they're running at the initialization rate, we can still set them. So now we can come down here, give ourselves a little bit of space, and set that to 0. Now we can say attack 1. Yeah. And you have to keep in mind that the amplitude of the audio file itself is decaying, and we're trying to fade that in. That doesn't change the waveform. I mean, it does, but it doesn't change the source of the audio file. So for example, if we did a really long fade in, it just doesn't, the amplitude doesn't get any higher. I mean, the envelope is getting higher, but the amplitude of the audio is getting lower, so they're kind of fighting with each other. But we can still bypass the attack. Let's have a nice crisp attack, or soften that just a little bit, or more. Okay, and then the release also, right, can be something like this. I forgot a comma, excuse me. Right, so now we have even more control. Flexibility is the name of the game with synth defs. When you're building a synth def, you really don't want to be thinking very much about the specific sound of the synth def, because a synth def doesn't really have a specific sound. It expresses a synthesis algorithm, which can be customized by providing specific argument values when a synth is created. So I think that's just, I mean, we could also go further and actually give ourselves arguments to control the curvature of the envelope segments, although that's kind of a, pretty detailed thing to do, and I don't think we're going to be desperate for that, although it's important to keep in mind. Everything else that can be modulated is being defined by an argument. So we're pretty much good to go here. And so now we have this great flexibility here to change sound in many different ways. We could also, we could even start later in the file. Need a comma after here. Yeah, kind of jumping backwards through the file as we go. All right. So, is there a question that I can help with?
Oh, does the after process end the comma as well? Or?
It doesn't hurt. But the problem was that I forgot this comma.
Oh.
And that's why it got mad at me. Because it sees that as this expression, right? Because it ignores white space. So, yeah. So you do need a comma after everything. The last one, you can, but you don't have to have a comma. Works both ways. The pitfalls of syntax. A lot of rules. Okay, how do we make this interesting? It's just a single ding, right? So one technique which should never be overlooked is iteration. Right? Do and collect in order to create clusters. Now, let me just to show this. This is, you would never ever want to do something like this, where, okay, let's make a normal pitch and then that one up a minor third, and it works, but if you want to make 100 voices or something, you're going to be scrolling for days, right? And you're like, oh, if there's a mistake in one of them, it's so. I think I've actually said this with iteration. If you find yourself doing something repetitive, stop and ask yourself, how can I use iteration to make this more efficient? So if we want to make this chord with -2, 3, 0, this little, let's just forget about all these and enclose this synth in an iteration block. Right? So we are going to do this array of 3 numbers and pass each number into the iteration block by declaring an argument, which is called n. So this function is going to be evaluated 3 times. On the first time, n is -3. On the next time, n is 0. And finally, n is 2. And we just plug n right in here. And let's bring up the node tree, just so we can see what's going on a little bit more clearly. Right? Okay, it's a good start. Everything is pretty constant in here, but you got to remember that this function gets evaluated 3 times, 3 unique evaluations. So we might want to do something like this. maybe a little bit more extreme. And if you listen carefully, but hopefully you can get a sense that each of the three synths has a unique placement in the stereo field. Like we could put them all, towards the right, or to the left. So we'll stick with this for now. Maybe we want to detune each of these a little bit. So this is just a playback ratio, which will change the pitch by the appropriate number of semitones. Why don't we also multiply this by another random, so basically this is going to be a random number between negative 0.2 and positive 0.2, and we're going to treat that as a value in semitones and convert it to a ratio, which is going to be something close to 1, but not quite. So it's going to take this pitch and just nudge it away a little bit. Right? It's nice. So many things we can do. We'll say exparand long release. Soften the attack a little bit. Here's an idea. N equals, okay, what if we want to sometimes make the whole thing down an octave? Right, we can say N equals N plus 0 or negative 12. Choose one of these. See, so we pass in the semitones value, and before we even make a synth, we're going to say flip a coin. If it's tails, go down by 12 semitones. And this applies to each of the individual three synths, actually. So it's not going to be the case that all three are always down an octave or not, but each one of those has the possibility of being down an octave, which is kind of more interesting, I think, than just shifting the whole thing. How would we do it the other way? If we actually always want these three to be in the same relative position, but the whole thing up or down an octave? It's a thinker. Right?
Can you do it inside the array?
Yes, it's something to do with the array. That is right. It's this here we need to manipulate, right? So we'll say this. Put this in parentheses. Plus 0, negative 12, dot choose. And we'll just run this by itself, make sure it's working. Yeah. So we're going to pick one of these two numbers and add it to the entire array. Yeah. So that's one option. I kind of like the other one, so we're going to go back to that. Kind of like a bass drum, right? Maybe a little bit of this to be cheeky. Yeah. What else can we do? Yeah.
How would you go about playing some of those samples backwards?
Okay, playing them backwards. Great question. Yeah, some of these want to go backwards. All right, so we're going to bump into a problem immediately because we start at 0. And actually, no, we're not going to bump into a problem because the envelope has the done action. So we've designed this nicely because we'll have to turn looping on. We'll just make a parameter for loop. So by default, it will not loop, which means if it goes backwards, it bumps into the start of the sample and just stops. So we'll run that synth-def, turn looping on. Okay, and then we want some of them to go backwards, which means we're going to have to multiply this playback rate, which is right now it's going to be some value like this, right? Or some value, oops, like this. We just need to multiply this by -1 some of the time, because that will make playback go in the opposite direction. So that is just simply, space this out on multiple lines, I guess. So this is 1, -1 dot choose. I think that should do it. Although here's what's going to happen now. They all start at start position 0. And if they go backwards, they're going to run into the very tail end of this prayer bowl, which is probably very, very quiet. So we're probably not going to hear anything. So I would be inclined to skip ahead by, I don't know, let's just start with 3 seconds or something. And again, this might supposed to be this might could. I forget if it's supposed to be the sample rate of the buffer or the server, but we're not doing rocket science here, so we can fudge the numbers a little bit. Okay, let's see what happens. Yeah, so it's like bumping into the attack. Let's make this random. And so random start position, somewhere between 2 and 4 seconds into the file. I'm not even sure how long this file is. Okay, it's 10 seconds. So that's great. So we're just, based on the randomized rates and the randomized start positions are going to totally screw up when the backwards ones actually bump into the beginning of the file. So it's going to be kind of a nice effect. I kind of like it. That's nice. Okay, let's do something like this. Okay, there's a musical scale, minor pentatonic. I do like minor pentatonic, so we'll say array.fill 8 notes. Scale.choose. All right, so what this does is it fills an array with 8 numbers chosen from our scale variable. Okay, so now we have 8 notes, and we might actually see a little bit of clipping here. I'm just going to demonstrate it. Oh, maybe not. I thought it was going to be a little bit louder, in which case we were going to turn this down a little bit. But it seems like we don't really have to. And I think this is because some of them are starting later in the file. I bet if we started them all going forward, all at the beginning of the audio file, that initial attack would probably create some clipping. But I think we're still in the safe zone. This is why you always work with your meters open. It's nice. It's like it's very Christmassy or something. Okay. What I'm just trying to demonstrate here is the freeform nature of experimenting with your code. You start with a synth that is maximally flexible with plenty of arguments to give yourself the ability to specify unique parameters or unique ranges, random ranges for parameters. And then you start with a synth. Right? And you think, okay, let's do a little cluster chord. So you use iteration, and pass in some pitch values as you go, and then just kind of experiment. I often find myself just dumping kind of random numbers in for each one of these and seeing what we get. Yeah, question.
So that where it chooses 8 things from the array.
Yeah.
If you wanted to choose but don't repeat it until all of them are. Kind of like it.
Oh, if you want no repeats?
Well, not until all of them have been chosen.
Ah, okay. So you want to sort of like pick all 5 and then start over? Yeah. Okay. Yeah, so how would we do that? We have this scale, and we want 8. I mean, okay, just so we don't ruin this, let's make a new thing here. Okay, so we have our scale, and because this is kind of a complicated operation, I'm not going to try to do it in one long line of code. Let's just make some more variables. So we'll make a COLL for collection. This is going to be our ultimate collection. And if we know we want 8, and we want at least, then you want to sort of pick these 5 until we run out. So we're going to have all 5 of these at least. And then we want to choose 3 more. So we'll say, we'll just first pick the first 5, right? I mean, and the order doesn't really matter here because we're playing a chord, right? If we were doing something sequential and we wanted the order, then this would matter. But you know, we set the collection equal to a scrambled version of the scale, right? And then we're going to say concatenate another array, right? And this is going to be so if we say like at 0, that gives us, here's our scrambled version, and then we've added another one, right? But we actually want not just one item, but an array of the first 3. Maybe there's lots of other ways to do this, but let me step outside of this for just 1 second. Let's say we have the array 10, 20, 30, 40, 50. And we say x at 3. Well, this is the number 40, right? X at 1, that's the number 20. X at 0, that's number 10. It's just accessing a single item. If I wanted to access a subset of the array, a sort of array of some of the internal items, instead of providing a number, you provide another array. So this means give me an array of the items at indices 1, 2, and 3. And you actually do need the double brackets here because this is going to be an error, I'm sure. No, it's not. It's ignoring the other ones. It says, okay, I'll give you the one at 1. That's not what we wanted. We wanted all of these items. Okay, so that's what I'm doing here. I'm saying randomize the array and then attach more items to the end of it, the first 3 of a scrambled version. And then we can just proceed with this. And, oh, you know what? No, we can't. We have to say call.do. Right? We have to apply this iteration to our new collection. Right. Right. So there's our collection. It chose, right, all 5, and then 3 more. And that's what you wanted, right? Yeah, okay. Yeah, good one. Good exercise. You can take a little time to unpack this one later. Yeah, it's great. Very wind chimesy. Okay.
Later on in this class, will we ever get to like a MIDI connection with SuperCollider?
Yeah, that is on the agenda. MIDI, getting MIDI data into SuperCollider. It's also possible to get MIDI out, but that's a little bit harder to demonstrate in class, I guess. We need some sort of device that receives MIDI. But yeah, we'll do MIDI in for sure. Okay. Let me transition now to filters. We'll augment this synth with some filters. And there are 4, if we're dealing with like the simplest types of filters, there are 4 kinds: low pass, high pass, band reject. Okay, so if we go into browse UGens and filters, there are 126 filter classes in my library here. Lots of crazy ones. Everything that has a plus classes is some extension that I have installed. But if we go up here to linear, we get some very basic filters. So here's BPF, that's the band pass filter. BRF is band reject filter. HPF, high pass filter. And LPF, low pass filter. And feel free to see what's in your library and mess around with some of them. Now filters, most filters are designed with some sort of internal feedback component which allows it to resonate, and as a result it's possible to blow up filters. It's one of the rites of passage of working with SuperCollider. So let's add a filter here. So we have our source sound, and let's say we want to apply a low-pass filter and then followed by a high-pass filter. So these filters, they start with the input signal, the signal to be processed, and that is, of course, sig. Right? Taking sig, it's a play buff. We're going to pass it through a low-pass filter. And the next argument is the cutoff frequency. So everything below is going to be more or less preserved. Everything above that frequency will be progressively attenuated. What should we put here? $1,000. And it's a trick question. I'm not looking for a specific number here. What kind of thing should go here? Yeah, one of these, right? An argument. If we put 1,000, then every sound produced by the SynthDef will be passed through a low-pass filter with a cutoff frequency of 1,000. And that will get boring pretty fast. So we will make an argument. And why don't we default it to 20,000 so that it passes everything? That way, if we just make a synth and forget to specify something for LPF, we'll hear the normal sound. This is good technique, I think. It's just providing sensible default values which effectively bypass the sound or give you some neutral or normal or regular sound. And then we can pass it through a high-pass filter. And we will set this one, make sure to give it a different name, to a cutoff frequency of 20 hertz. So it passes everything above 20 hertz. And so this shouldn't sound any different. This 11, so cheeky. Okay. So if we say LPF 500, oh yeah, it's very nice. It does take the amplitude down quite a bit, but it's a totally different sound, right? It's round and warm, makes everybody a little sleepy. And we can do the same thing with the high-pass filter. Just give us the wispy bits. Yeah, and we can do these sort of together. Like let's say 1,000 for the high-pass filter and 6,000 for the low-pass filter, and we're essentially reverse engineering a bandpass filter here. We could just use BPF, but this would also work. And I think it's fair to say that filters are not, they're not gonna, it's not a magic wand that turns your sounds into this amazing thing, right? They're just a tool, and they do what they do. And really a lot of the kind of compelling, interesting stuff is how you actually execute these sounds in your code that generates synths. A lot of times I see new students making a SynthDef and kind of focusing on the SynthDef as if this is the composition, right? And kind of composing the SynthDef to make it sound really cool. But really all you're doing is just like changing a default value. You're not really, you want to give yourself maximum flexibility, not to put too fine a point on it, so that down here you can be very precise with your algorithm so that you control your ranges and your numbers all very nicely to make interesting sound. Okay, let's talk safety for a second. Filters can blow up if you do something irresponsible. Here are a couple rules to keep in mind. Any kind of cutoff or center frequency value in a filter should be between, I'd say, no lower than 20 hertz and no higher than the Nyquist frequency, which is, 20,000 is going to be below the Nyquist frequency of a sampling rate of 44,100. So if you ever sort of find yourself plugging in some modulator here or something where you're not sure what the actual value is going to be, it never hurts to clip between 20 and 20,000. Just take this value, whatever it is, and then constrain it. So if it's greater than 20,000, it's equal to 20,000. If it's lower than 20, it's equal to 20. A hard boundary between these two values. Normally in the world of audio, we think clipping is bad, right? But this is not the signal we're listening to. This is just a number that determines the cutoff frequency of the filter. So it's very smart, in fact, to clip this. That way, if we go down here and we're like, wee, right? No problem, right? I mean, I think if you make a really, really, really big number, it's just like, it's not going to be able to represent the number correctly because 32-bit precision issues. I don't know exactly what the deal is, but yeah, it's just if you accidentally I don't know, do a negative sign or something, right? Negative numbers, that's a great way to blow up a filter. Filters always blow up if you give them negative numbers, right? It's just some sort of internal recursion that just spirals out of control.
Is it too dangerous to hear what it sounds like?
Yes, it is too dangerous. Just because I'm recording this lecture and I tell you, we'll do it after class. We'll blow some filters up. We'll mute the audio system and you can watch it on the scope and see exactly what happens. But we're not going to blow up any filters now. Anyway, these I think are great to get started with. I'm not going to spend too much more time on these, but the only thing I do want to point out is that in BPF and BRF, the pass and reject filters, in addition to a center frequency, which is the region being processed, there's also a parameter called RQ, which is short for reciprocal quality. In the world of filters, many filters, band pass and band reject included, they have a factor called quality, which determines the width of the band. High quality means a narrow band. Low quality means a broad band. So like the lowest sort of theoretical quality is 1, and then you can kind of go up towards infinity and the band gets narrower and narrower and narrower. SuperCollider, as a sort of little efficiency optimization, asks the user to provide this value as a reciprocal, so 1 divided by the quality. So 1 is again the lowest possible quality, and as the RQ value gets closer and closer to 0, the quality increases. So back to our main point here, which is being safe with these values, this value should always be less than or equal to 1 and greater than 0. Right? Don't set it equal to 0. Don't set it to some negative number. Don't set it to like 4 or 20 or 1,000. Right? Between 0 and 1 and never equal to 0. Your ears will thank you. Okay, we're getting close to being out of time, so I don't think we'll do granulators today, but we will, I'm sure, touch on some granulators before the end of the semester. I'll tell you what, why don't we spend 5 minutes with a little bit of a teaser about next week. So we have this code here. Make sure I didn't blow anything up here. Let's go ahead and clip this as well. Right, there we go. So now our filter values are safe. Right. And just to demonstrate, let's make that 1. So if I start dropping this value, we'll still be safe. And let's even poll these just to be extra sure. So I want to actually see these values as the synths are created. I think we're going to see a ton of them here because we're making 8 synths here. But if I drop this to 10, it's still 20. See, we have clipped the value, so we can even do something really, really dangerous, and it's still 20. I mean, if we didn't have that clip in there and we, for some reason, lost our minds for a second and decided to put some negative numbers in here, if we didn't have that clip there, we'd probably, something nasty would happen. And as much as I would like for there to be safety measures in place to prevent you from doing stuff like this, it would not be in the spirit of a programming language that gives you full power over these things. So it's, as my advisor used to say, it is not infantilizing. It assumes you know what you are doing. Okay, so let's talk about sequencing for just a little bit. I'm gonna go back to a simpler version here. And let's get rid of this for a second. This, and get rid of this as well. Okay, back to an earlier version with just our three little chords, or sorry, our chord with three notes. And now the question is, my question for you is, how do we make this not a chord, but a melody, or an arpeggio? How do we get SuperCollider to go ding, 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 instead of bring? Now, here's how we do it. There's a class called routine. This is how I like to introduce sequencing in SuperCollider. Routine is a function which can pause in the middle and resume. So what we can do here is put the whole thing in a routine. Like this. And if we then play the routine, it's going to be the same. But once we are inside a routine, we are allowed to wait for a duration. And you can do this one.wait, or you can say wait one, where there are two sort of argument styles here. And now watch what happens. We have a sequence. Say, right. Yield also works. It's just a synonym. I think yield is more ubiquitous, but wait, when applied to numbers, wait and yield do the same thing. Another cool thing about routines is that you can say next. Now what next does is it just starts evaluating, and as soon as it bumps into a yield, it just stops. It doesn't treat it as a duration. It just says, oh, this is a pause. I have to pause here, right? And it just hangs out. And then we say, okay, go on, right? Next one. And it gets to the end and it says, I'm done. There's nothing else, right? I've done everything there is to do. This, all right, this is bothering me. We're going to get rid of this poll. Right, so we make the routine. Next. And if we want to go back to the beginning, routines can be reset. It just rewinds the tape. Reset in the middle. Yeah. And so next just goes and uses the yields as checkpoints, and play will treat the yield times as durations, as rests, basically, whatever they happen to be. All right. So put that in your hat and stew it around for a bit, and we will come back to this next week and use routines to transition into events and streams and patterns and p-bind and all sorts of cool algorithmic sequencing stuff. Okay? So your homework is due a week from today, and I'll see you all next week.